Well, howdy, howdy, students. This is going to be, 13.3. We're going to look at something called Lechatellier's principle today, and we're going to see how things affect equilibrium. Equilibrium can change. We can shift it to the reactant side. We can shift it to the product side. We can not change it at all. So what we're going to look at are these four factors that change equilibrium. We call it Lechatellier's principle. So Lechatellier's principle is all about how stress added to a system changes equilibrium. Now, in real life, when we have stress, we end up changing to alleviate, avoid the stress. That's how we're designed as human beings. Now, chemical equilibrium is kind of designed the same way. It's going to shift in the direction that's going to relieve the stress that's been applied. So the first change we're going to look at is a change in concentration. We can add more of reactants, we can add more of products, and we're going to look at how that shifts equilibrium. So if we increase the concentration of a reactant, it's going to cause the equilibrium to shift to the right and form more products. You add things to the left, it's going to go right. If you add more product, if you increase the concentration of the products, equilibrium is going to shift to the left. You add something to the right side of the equation, it's going to form more reactants on the left side. Now, if you decrease, it's the opposite. If you decrease the concentration of the products on the right side, well, it's going to shift right to fill in what's missing. If you decrease the concentration of the reactant, it will fill in and shift left to fill in what's missing on the reactant side. So, if we summarize what happens when we change concentration, I'm going to say A plus B, and with equilibrium, we have a double-sided arrow, yields C plus D. So if I increase the concentration of A, what we're going to see is that equilibrium shifts to the right. If I decrease the amount of reactant B, equilibrium would shift to the left. If I increased reactant C, equilibrium would shift left. And if I decrease product D, I will shift equilibrium to the right. So consider a bathtub. This is a good analogy that we like to use in chemistry class. Here's our general reaction that I just mentioned. Here's the beautiful bathtub that Mr. Cantu drew. Such an artist. If you remove A or B, it's as if you're scooping out a little bit of the reactants on the left side. Nice square pail. We scooped out some water. There's a hole in the left side of the bathtub. So what happens is water is going to flow to the left to make up for the difference. Now, if we add C or D, we add more water to the bathtub, and equilibrium is going to shift left as well to fill in what's low or what's missing. If we remove C or D, we take our square pail, scoop out more water, and what we find is that equilibrium will shift to the right to fill in the hole. If we add A or B on the left side of the bathtub, it will shift to the right to fill in what's low. So a real example would be with real chemicals. If we add the compound CO, we would be shifting equilibrium to the left. If we add carbon on the left side, we would shift to the right. If we add AS4O6, which is a reactant, we're going to shift to the right. And if we remove AS4, which is a product, we'll shift to the right as well. The second factor that affects the shifting of equilibrium in Lechatellier's principle is the change in temperature. How does temperature change affect equilibrium? Well, we're going to treat energy as a product or a reactant. And just a reminder, we usually see energy in the form of joules or calories. Specifically in this unit, we're going to see kJ, which is for kilojoules. Okay, and then once we know what side of the reaction energy is on, we can treat it just like factor 1, concentration. So an increase in temperature of an exothermic reaction, where delta H is a negative value, is going to cause equilibrium to shift to the left. A decrease in temperature of an exothermic reaction, again, delta H is negative, will cause a shift to the right. An increase in temperature of an endothermic reaction, where delta H is positive, will cause equilibrium to shift to the right, and a decrease in temperature of an endothermic reaction will cause equilibrium to shift to the left. A lot of words. This is a reference. Make sure everything's filled into your notes here. We're going to apply this to some real-life examples here. So here's our real-life example. N2 plus O2, both are diatomic. We're going to form nitrogen monoxide. We are given the enthalpy value for the reaction, and what you'll see is that it is a positive value, which means endothermic. So what happens if we add heat? What happens if we remove it? We lower the temperature. So what we need to know for this problem is where the heat goes. So when we have a positive value for delta H, we are going to place the energy on the left side of the equation. Energy is a reactant here. So if we're adding heat to this, we're going to be increasing the amount of energy on the left side of the equation. And if we're adding things to the left side of the equation, we shift to the right. Now, if we lower the temperature and we take away heat from the left side of the equation, we will shift equilibrium back to the left. So the key here is knowing which side of the reaction delta H is on. That's key. Endo's on the left, exo, heat is on the right. So here's an exothermic reaction. You'll notice that we have a negative delta H, which means it's going to go on the right side of the equation. So when we increase the temperature, we're adding more of this product. This is a product now. You'll notice that we do have a positive sign. The delta H is still negative for the reaction, but it's because heat is being released, which makes it a product. If we remove heat, we take away a product, it's going to shift to the right to fill in the gap. So here we go. The reaction's been given to us. If we decrease the temperature, we're taking away some of this reactant, which would cause equilibrium to shift to the left. What we are not given here is the delta H. So we could ask you, what is the delta H? It would be a positive 556 because it's a reactant. And this tells us that this is an endothermic reaction. Energy is required for this reaction to take place. Okay, factor number 3, changes in pressure. Changes in pressure only affects equilibrium systems that have, keyword, gaseous products and or reactants. Increasing the pressure of a gaseous system will cause equilibrium to shift to the side with fewer gas particles. So we're only concerned with this symbol right here, gas. Decreasing the pressure of a gaseous system will cause equilibrium to shift to the side with more gas particles. So if the system has the same number of moles of gas on each side, pressure will not affect equilibrium. And so when we're looking at the moles, we're going to be looking at the coefficients. If we add an inert gas, it is not going to affect the equilibrium because the partial pressures of the gases involved in the reaction will stay the same. Inert gases generally don't show up in the reaction at all. So if we say that we add one, it's not going to affect the actual reaction that's taking place. So here's our real-life example. P4 plus Cl2 yields 4 PCl3. So let's look at what we have here. We have a solid here, we have a gas here, and we have a liquid here. So the only thing that we're actually concerned with for pressure would be this guy right here, which is a reactant on the left side. So if we increase the container volume, we have to understand what that does to the pressure. So let's refresh. PTV. If we are increasing the volume, and we're holding temperature constant, the pressure will go down. So what we're actually saying here is that we're decreasing the pressure. And because we have more moles of gas on the left side of the equation, we're going to be shifting equilibrium to the left. So just a heads up, this tends to be the most complicated concept for students to understand. If we decrease the container volume, that would be an increase in pressure of the system. And in this case, it's going to shift to the side that has fewer particles, which would be the right side of the equation. And if we add argon, which is AR, it's not going to change our reaction and thus does not actually change anything in the system. Now, if we actually are adding gas, when we add gases to a container, that does increase the pressure, but because it's a noble gas, there is no change. Okay. Another example here for pressure. PCl3 plus Cl2 yields PCl5. We have a gas in several different places. 2 on the reactant side, 1 on the product side. So total, we've got 2 moles of gas over here because these are both 1 coefficients. And there's also a 1 here, so there's 1 mole on the product side. So if we decrease the container volume, that's increasing the pressure, which would shift to the side that has fewer particles. If we add helium gas, that's inert, that's a noble gas, so no change. And then we have another reaction down here, PCl3. We've got 4 different species of gases, 4 moles on the left side and 4 moles on the right side. Again, where did that come from? There's a 1 here and a 3 there, which makes 4, a 1 and a 3, which also makes 4. So it doesn't matter what we do to the pressure, there will be no change if the moles are the same on both sides. And the last factor, this is where we're going to stop for today, addition of a catalyst. Adding a catalyst does not affect equilibrium. So there you go. Short, sweet, and to the point. If you add a catalyst, it only speeds up the reaction. So the rate would be affected, but not equilibrium. So we're going to put things together here. All 4 factors together. And you're going to have to differentiate between the 4. So here's our reaction. We have a delta H value of negative 41 kilojoules. So what I'm going to do is I'm going to add 41 kilojoules to the right side. I'm also going to point out the gases. I've got 2 moles of gas on the left side and 2 moles of gas on the right side. So now we can answer our questions. What if temperature is increased? Well, if I increase the temperature, I'm adding more heat to the right side of the equation, which is going to shift equilibrium to the left. If I add an inert gas like helium, which is in group 8, group 8A specifically, no change there. If water vapor is added, which is H2O as a gas, which we do have in the reaction, we're adding more to the left side of the equation. The concentration's increasing, so we're going to shift to the right. Gaseous carbon dioxide is removed. Now that's carbon dioxide, so we're talking about this product. If we remove this, equilibrium is going to have to shift to the right to make up for the loss of concentration there. And if a catalyst is added, there will always be no change for the equilibrium. Another example, we have 2 moles of gas on the left side and 3 moles of gas on the right side. Delta H is a positive value, so it will be a reactant in this endothermic reaction. So if oxygen gas is added, we're increasing the concentration, which will shift equilibrium to the left. If pressure is increased as we decrease volume, we're going to shift to the side that has fewer moles of gas, which would be to the left. So we would be moving from 3 moles to 2 moles. Argon gas is added, no change. Temperature is decreased, which means I'm removing heat from the left side of the equation. It will shift left to make up for the loss. Gaseous sulfur dioxide is removed. If we take out sulfur dioxide, equilibrium will shift to the right to fill in for the loss. And that will do it for this video.